So guys, any questions? We can dive straight to it. Go ahead. If you want to put your question on the chat, that's also fine. I can try to monitor that. All right, 1C and 1D for the example exam. Sure. So once, if you look at the sample exam over there, let me see. I can go solution directly, 1C and 1D. Yeah, I think of course the detail you guys will really have to dive into it. I can talk about them at a high level. You can tell me specifically which part you got question. I think that'll be a nice way to follow up. Okay. All right, so this is one type of question. You want to state formally the proof obligation for the loop. And here we talk about the loop invariant being maintained, right? So this is the part you want to go back to our last lecture. Let me just show to you which part you want to go to. So if you look at, for example, the iPad notes, you will see that over here at the end, we spoke about the proof obligation for the loops, and the one on the example question, there's just one of them, right? It's about maintaining the loop invariance. So we say that assuming that the loop invariance and the condition for the loop are actually true, and then executing the body of the loop, we're gonna maintain the loop invariant that remain to be true. And the whole thing is actually specified as a Hoare triple. Right, so that's what we spoke about in the class. And the example question just gave you one. If I gave you other conditions to really formulate, you should also know how to do them, right? Just as an example. And if you go back there, you will see it's just about putting things in the right placeholder, right? So this part over here is the precondition over here. Oh, beg your pardon. So A here is just about you were not asking about A. Sorry, just give me one moment. I want to make sure I only open one, otherwise get myself confused. Okay, good. So this one is about loop invariant being maintained over here. So you will see that you want to make sure it's maintained. So that's loop invariant over here. Okay, and then I noticed that, okay, so this one here is about I less than or equal to length input, right? So that one there, you can also go back to the code over here. So that one is the condition for the loop, right? So that one is included. You can think about this part here. Okay, let me just go back here. So this part here is the B, right? And this part here is the I. And you want to make sure the same I is also maintained as the post condition for the Hoare triple. And then we say that this is the body of the loop. You just basically copy, right, the body of the loop, which can be found over here. Right, just right here, right? So the body of the loop is actually a sequential composition, and the first phase is like an if conditional, and the second phase is like a variable assignment, right? We also spoke about the different scenarios of the implementation, so you really want to review the various rules, the various scenario, and see how you can do the sequential composition. All right, so that's 1C, right? And also it is important whenever you actually got let's say tuple indexing over here, for example, you can see we got tuple indexing over here. So you got to make sure this particular indexing is also valid. So in the programming sense, you don't really run into array index out of bound exception. So to really do that, you can just amend by adding another constraint to make sure the J over here is actually a valid index for the input tuple or input array. All right, so that's 1C. And for 1D over here, it's a giant proof, but it's really something. That's why I kind of put the challenging one, for you guys to try, as an example. I can go over them very quickly at a high level, but you really want to dive into the details to see how things will work. Okay, that one there. Let me just switch to iPad over here. Okay. All right, so that one there, you want to, so that's for part D, right? Assuming that you're already kind of familiar with the question itself, or you can just maybe come back later to a recording once you have tried the example yourself, okay? So there are different phases over here. So here, first of all, we want to calculate what's the WP for the body of the loop to maintain the loop invariance, right? If you kind of remember the condition there. So let me put it here. So you got the exit condition, the condition for the loop, and also the loop invariant I, and then you got body of the loop, which should maintain the loop invariance, right? So first of all, we want to make sure the WP is there, right? We want to calculate that. So what you want to do is you want to calculate the WP for the body of the loop to establish I. So once you calculate this WP over here, you want to make sure the actual precondition is no weaker than that. So that's where the implication we get a proof. So these are the two phases that we spoke about in the lecture. So doesn't matter how complicated the question might be, you always gotta follow the same steps. All right, so really to calculate this WP here, right, it's basically like a sequential composition over here. So you have to deal with this one here first, right here, right? And then followed by this one over here. Oh, sorry, the second one is actually if conditional, right? So think about the yellow part here is the first one to calculate the WP. And the second one here is the second one. This orange one is the second phase. So what we do is you gotta watch out for the substitution over here. So you can see once we got the first WP rule, so this is based on the sequential composition rule. And remember the swap program that we did in the last class. You want to review that one. That one there really give you a very good idea how to organize the rule. Okay, and for this one here, this will be the very first phase. So we got I plus 1. Sorry, let me use a color here. So there's I plus 1. And then that one there is going to be used to replace over here the I. Okay, so you got to replace every free occurrence of I, because now we are replacing the I by I plus 1. So after that, you can see that if you try to replace I over here by I plus 1, so I plus 1 minus 1 is going to give you I. Okay, so that's why you got I over here, right? Just simple substitution and do some simplification. And once you get to this part here, you can now see this is the remaining phase for us to handle, right? So that's a remaining phase. And for this remaining phase here, you can see this is an if conditional. So we gotta talk about either this condition here is true, or this condition here is not true. So I just say not the case, larger than is going to be less than or equal to. So we got either this one here or this one here. And each one of them is going to execute the corresponding branch to establish this particular post condition over here. So if you go for this branch over here, result is going to be assigned to input J, right? So this is one way, input J over here. Or think about if the condition here is not true. In that way, result doesn't really change. And if the result doesn't change, it's as if it's simply assigned to itself. So this is a little trick you can also learn from this example question here, right? It's going to be a result, right? You go for either way. So now you just got to find the substitution. So you can see result is going to be replaced by either this or is it replaced by this. You're going to replace the free occurrence of result right here. Okay, so these are the two places you're going to watch out for, right? So you can see this result is replaced by input I. And this result here is by just result itself, explicitly, right? So either here or here. All right, so once you have done that, so this is the result for the WP calculation, right? So that's a step number 1, right? This one here is nothing about proof. It's just about applying the rule appropriately. So you got to make sure every step of your rule calculation is well justified. You got to mention which rule you're using for the WP, right? And don't skip the step. You want to make sure every step is shown properly, so we will be able to grade it properly. Okay. All right. Any question about step number 1 before I move on? All right. All right. For step number 2. You want to somehow make sure, so we already calculated the WP over here, and we want to make sure this precondition here will imply the WP that's calculated, right? So the proof itself, I'm just gonna highlight certain steps that you want to watch out for. Otherwise, it's not a difficult one. It's just a little bit long, but that's exactly the chance you can practice about doing some long proofs yourself. Okay, let me just highlight certain parts that you can watch out for. Okay. Okay, so first of all, you can see here we want to make sure this part here is the B. Okay. This part here is the loop condition. And this part over here is the looping variance. Looping variance. And this part over here is the, and this is the WP that we just calculated. And we're only proving about the left one over here. And to really prove the other one here, you can prove them separately. So we're going to prove this one here in here. And to prove the right conjunct over here, it will be very similar, and you should really maybe try that as an exercise. Okay. All right, so this one here is really corresponding to right here, right? So how do we prove it? So the whole thing is you want to prove something about implication. So we just want to, so here we got nested implication. So you can see we got this one over here, and also this one over here, right? It's nested. So we can use a rule from 1090 called shunting. So if you actually got nested implication, you can simply combine these two implication into conjunction. All right, you can review the rule or put on your data sheets if you want. And that one there, we're going to combine 1, 2, and also 3. 1, 2, and also, okay, let me do it again. 1, 2, and also 3, right? It corresponds to 1, 2, and also 3. And we're putting conjunction between them. And we only got one implication. We got rid of the nested implication. And that's what we want to prove right here. So this one here just corresponds to this one right here. Okay, just to make sure the big picture is clear to you. And the way we're going to prove it is by assuming the antecedents. So we're going to assume that we got this, and we got this. 1, 2, and 3. So we're going to start with the expression here as a consequence, and then at some point we're going to use either this, or this to really prove it. Right? That's really the spirit for assuming the antecedents. And we actually start with this, and then you want to watch out for the first lemma we're using, which I'm pretty sure I have seen before in maybe 1090. So here we say J should be range over 1 to I. So we can split that into I minus 1 and also I itself. So that means we're going to replace every occurrence of J over here just by I. For example, you can see J here, and also J here. So that's why you're going to see right here I, and also I. Right? So we can split this single expression over here into two. So we got number 1 over here, and also we got number 2 over here. For number 1 here, it corresponds to 1 until I minus 1 inclusively. And number 2 over here just corresponds to I. Right? Split them. And we're going to prove them separately. Okay? And then this part over here is something that you have to also convince yourself. We are basically using different parts of the antecedents that we assume. Okay? So let's see where they are. So this part over here is input I larger than result, which is right here. Give me one moment, right here. Input I larger than result, right? So if I can also just show to you. So think about this one here comes from one of the antecedent that we assume, okay? Or if you want, we can also, I can show you also another place over here. Oh, sorry. Let me do better. So it's input I larger than result right here, right? Right here. We're just using one of the antecedent we assume. So there's one thing you have to consider. Another thing you want to consider is this whole thing over here. Okay. So for that one there, you can see that that one there is going to be right here. All right, let me highlight it. And that's also the one that we're using. So you want to convince yourself this one here combined with this one here is actually going to show that this one here is actually true. Okay, so I'm going to write it down for you, and then it's actually quite obvious once we write it down. So you want to look at this part over here. This is something you want to prove, right? Within this particular range. And then what we are saying is, so we say that, first of all, we start with this one here. So we got input I larger than result. And also we got this one here within this particular range, right? I minus 1, right? It's actually matching the range right here. So that's why we can kind of use the assume antecedents. And also result larger than or equal to, oh, sorry, let me just write it down underneath. Okay, and then we got result larger than or equal to input j. So what you got is input I larger than result. Result itself is actually larger than input j. So by transitivity, we know that this one here must be larger than equal to this one here, right? So this one tells you by transitivity, input I should be larger than or equal to input j. And this is what we wanted to actually prove. Okay, this one here. Okay, so that's why you will see true right here. And then after that, if you look at just this part over here, that remains just from here, right? That part here is actually quite easy to justify because input I, A must be larger than or equal to itself for any number. So that's why it will be true automatically. But you're just going to make sure you write it out explicitly as a justification. Okay? So there's a high level about how we actually understand this proof. Of course, you want to do that by yourself too, to practice. So we don't really do nested while loop, as I said in the last class. Okay.
Okay, sir.
Yeah, go ahead.
Are you able to go over a question from written test 2? Is that possible?
Sure, of course. Which question are you talking about?
It was the question where it was pretty much rank the formulas from
okay.
promise.
Okay, sure. We can do that. About which one's strongest, right? And which one's weakest?
Yes, sir.
Sure. Just give me one moment. So we got written test number 2 over here, and then so preview the quiz. I guess this one you're talking about, right?
Yes, sir.
Okay, sure. Let me just finish the attempt and submit, and then we'll see. We'll look at the answer together. Okay, so this one here. So this will be the correct order right here. Okay, so let's now take a look. And we'll go from the strongest to the weakest. That's basically what we're doing. I'll set it up and then I will talk about it. Okay, so let's now talk about that one there. So this is the strongest one. And this one here is the weakest one. Okay, so this one here requires that every state must satisfy phi, right? That's really the strongest one, right? We are requiring that every state must satisfy phi. Okay, and then this one here is slightly weaker because we're saying that at some point in the future, for example, let's say this one here could be that we require maybe only starting from the third states, we're going to satisfy phi. In which case, what comes before, we don't really care. So that's why that one is weaker. Okay, and then this one here about future, right? So that one let's say future state phi, and that one is even weaker because that one doesn't even exist. That after phi is actually true at some point, what about afterwards and before that? You don't really care. As long as there is a future point that will satisfy, you'll be okay. So far 1, 2, and 3 is obvious that this one should be the strongest one, and then this one here and this one here. Okay, what about this one here? Okay, this one here, you can see there's an implication, right? So we're going to evaluate, try to see if we can evaluate this implication, if we can simplify that to something shorter so we can consider. So you can see this one is about global, which we just spoke about. And this one here is about future global, at some point in the future. We already know this is guaranteed to be stronger than this one here. So that means this implication here, it would just be true. Because we're having something that's stronger implies something that's weaker. And of course, the implication would be just true. So what we can reduce is this number 4 here is just true. And true is really always the weakest predicates. So that one should really appear at the bottom.
Perfect. Thank you.
Okay, no problem. Yeah, no problem. So that one, yeah, if I give you something similar, now you will know how to do it on the exam. Good. Just about the level of difficulty, I would say for, let's say for program verification, I think it will be more or less similar to what you will see in the exam. Of course, there might be some minor extension, but I think that will give you a pretty good idea about what might appear in the exam. For other questions there, I didn't put many for the example, but I should really go back to the basics about the principle we discussed in the class about LTL, about math review, all kind of stuff. Okay, how do we compare binary and unary operator in terms of being stronger and weaker? I think a very good way to get some intuitive sense is to think about like what I just did, right? To think about for each pattern over here, what's going to be the requirements for the phi to be satisfied, right? And then think about the stronger the formula is, that means the fewer model or path is going to satisfy that. For 1090, I would say that our math review and also any additional properties or exercises that we spoke about in the class, that should be sufficient, but it doesn't hurt if you want to review some 1090 stuff. What would be the overall difficulty compared with written? You know what? It's really hard for me to measure that because they have different coverage, and also exam naturally will be harder because it covers everything. Yeah. Another question about what if they are nested together? Are you talking about the temporal operator being nested together? Right. So for that one there, why don't you take a look at, okay. That one there, we actually spoke about quite many examples in the class, right? So for example, you can go back to, right? You can see here, for example, on Wednesday, March 19th, we talk about how we can consider nesting GF and also versus FG, right? And also we look at this particular pattern over here with the implication, right? So these are all the examples you can look at. Yeah.
What if the unary and binary, they're nested together, not just temporary?
You mean the unary and binary nested together?
Yeah.
I think the principle will be the same. So you have to kind of see the formulation for the operator, and then well, I don't really have any example on top of my head. Let's see this. Yeah, something like this. So let's say, for example, you might say future, and then let's say phi 1. Let's say until phi 2. So you definitely want to get down to the basics about understanding this nesting over here. I presume that's one of the example of what you meant. So you can definitely try with this one here, because this particular nesting here is supposed to be something that should be satisfied at some future point. Okay, so you would say something like there exists some I, and then you should say something like I larger than or equal to 1, and also pi I will satisfy. So let's say here, phi 2. This could be phi 2 over here. And of course, for this phi 2 over here, you have to somehow also apply the definition for the until, right? It's more like a nested quantification, right? So here you want to also apply the definition of the until operator. And the result should be like a nested quantification.
Sorry, shouldn't that shouldn't it satisfy phi 1 and not phi 2?
Oh, sorry, when I say phi 2, sorry, I beg your pardon. Yeah, you're correct. So when I say phi 2 over here, I really meant the whole thing over here. Oh, sorry, use the wrong thing. Let me say it again. So the green one, the green box over here is going to be some formula that should be satisfied by f. So you can think about the skeleton I have written so far is only for the future operator. So you want to say that there exists certain I, and then pi I should really satisfy this whole thing over here. And for that whole thing, you should really unfold it using the formulation of the until. That's what I meant to say. Can it make sense to you? For that one there?
Yeah, Professor, could you please provide the unfolding sector? I'm confused as to where the states lie after unfolding.
After unfolding?
Yeah.
You know what? I would say for this one here, I can write it more properly, maybe offline. Maybe try it out yourself, and then I can maybe release this particular one, maybe after the review session. I can do it by the end of the day.
Okay, thank you so much.
Okay? Okay, yep. All right, any other questions?
I have a quick question about the math review.
Math review, of course.
So I was kind of surprised when I looked at the practice test and I noticed that math review was used on one of the questions. I was like, let me see if I can find it really quick.
Mm-hmm. Well, you want to tell me the slide number, or?
It was yeah. Sorry, I don't have the
Sure. You mean the math review lecture specifically, right?
more so related to like the question on the practice test that used math review.
Okay, so which one should I go to? Or you just have general question?
It's more so general question.
Go ahead. Yeah, go ahead. Yeah, yeah. Mm-hmm. So what's the general question?
Oh, I was just wondering how much of the math review should we put on our cheat sheet, because I was kind of surprised myself.
Oh, I see.
Mm-hmm. Like the definition of, I think it was an existential quantifier or.
Yeah, well, I think that these are pretty. Well, I think the math review themselves are really about practical logic and propositional logic. Of course, I would tend to think for the very basic definition for implication, or maybe especially for implication, it may not be necessary for you to put on the data sheet. You might have understood it pretty well. Maybe for the also for this basic definition for all exist. If you want, maybe you can put, well, if you really feel comfortable, don't feel comfortable about some basic lemmas or theorems. For example, you can put contrapositive, in the data sheets, or there are other theorems that if you don't feel comfortable, you can also put them on the data sheets, right? It's completely up to you. If you feel comfortable about the basic ones that we mentioned in the review, you don't really need to put them. But I would say maybe in the practice question there, I definitely we're definitely using something that's kind of outside the scope of the math review. For example, shunting, now you know it. You can definitely put it if you find it useful, and also how you can split the range, and also assuming the antecedent. So these are all the important stuff that you should know, right?
Right. I think it was the proof obligation question. It said there's a part that said arithmetic in the solution.
About arithmetic.
Yeah.
Okay, let me
I
just
think it was just.
let me just go there and then, yeah. So give me one moment. You mean right here, right?
Yeah.
So which part? Sorry, which part are you talking about?
I think it was question 1B.
1B. Okay. Oh, you mean here? Yeah. So arithmetic is really something for you to, just to, for example, if you go from here to here, let's see what the change is. Yeah, you can see here, we just go from 1, 0 to false, right? So this one here is not, I think arithmetic in some ways is a little bit vague. What you could have said would be, because 1 to 0 is empty range. So that's why this would just be equivalent to false.
Right. And also for question 2, I saw there was a known theorem for all x. I guess we should probably put that on the cheat sheet as well.
Yeah, that one, I believe I mentioned that maybe in the one of the math review or the exercises we did. Remember there was a exercise we did to actually prove the conversion between for all exists. I believe that one was mentioned there. So if you can definitely feel free to review that part. If you still don't feel exactly comfortable of recalling that instantly, you can definitely put it on the data sheet as well.
Okay.
Yeah, good. One-sided, yes, that's correct. One-sided. You can handwrite it. You can also type it, or you can take screenshots. You can also put diagram. That's all fine.
Professor, I had a question.
Yeah, go ahead.
So say if we have nested if conditions like this one in chat. Just a second.
Yeah. Nested. Oh, you mean not nested loop, but nested if, right?
Nested ifs, yes.
It's it's definitely possible. I can give you a quick example, give you some idea. Okay, so for example,
would we have it broken down to like an example in chat? So would we have like 4 conditions, or would we have like 6 conditions?
Okay, I can put that on the iPad. Let's say if we got if, let's say Boolean condition 1, and then if B2, and then you got else B3, okay, and also you got else over here, B4, yep, actually it could be else if, but anyway, so I think else should be good enough. B2, B3, and then like that. Okay. Let's say if the code is actually what you're given to prove correctness is about this. So why don't we start with you? How many conditions do you think we need to handle this? To kind of flatten the nested structure. 4?
I was thinking like 4.
You think about 4? Okay. That's pretty good. It's also that should be quite some conceivable. Okay. So here you can think about if you're given something like this, you can flatten out the structure to be. You can say, okay, so thinking this way, think about the different branches you're going to go to. So branch number 1, you can go to branch number 2, and also branch number 3, and also branch number 4. Okay, so what we can do instead is something like, so we can say if, so now this part here is going to be B1 and also B2. B1 and also B2. And in that way, we're going to do whatever the green one is going to do. And then we can do else if, just different condition there. And then for that one there is going to be B1 and also not B2. Okay, and that one there is going to be here. And then you see the idea. Else if, and then we can do, let's say this will be not B1 and then B3, not B1 and B3, and that part there would be the pink one, and finally, and then we got this part here. Okay, so that would be basically not B1 and also not B3, right? Very systematic. So let's say once you flatten out the structure from here into here, so now to apply the WP, you can say this condition here implies the WP for this one here to establish the post condition, and etc. And then you're gonna conjoin all the WP together.
Okay, thank you, Professor. And something like this is possible on the final exam.
Yeah, well, now that I already talked about it, right? And you can see it's not difficult, right? So it's possible. I wouldn't say it will be, but it's definitely possible. Yeah.
Okay.
Yeah. So nothing outside the lecture and some, I wouldn't say that, because 1090 in some way is like implicit, right, prerequisite to this course. You don't necessarily have to review the entire 1090, but I would say the basic proof technique, like the lemmas we're using, it doesn't hurt to review them, but it's up to you, really. All right, any other questions?
Hello, Professor.
Go ahead, please.
So I have a question about the priorities that the logical operators have.
You mean the precedence?
Yes. So does conjunction and disjunction always have precedence over implications if there are no parentheses?
Right, so okay, negation always got the okay, so if you talk about precedence, okay, so we talk about the tightest, right? The tightest one is always negation, and then you got conjunction, and then you got disjunction, and then implication, and then also you got equivalence. So this one is the tightest.
Okay.
Yep. So for the solution to exercises, I can show you guys. Okay. Right. So you can see that on the lecture side, let me just refresh the browser. Okay, you can see I got some loop correctness. That's the one we did in the last lecture. That one is already there. And also you can look at the until, weak until, and release operator. That one is also there, right? 2 exercises, right? I think they were there. And the one that your fellow student just asked about, nesting binary and unary, that one I will also post that maybe when I post the recording later today. Right, just about the precedence for temporal operator, if you can just go over, I think it's one of the earlier lecture when we talk about the syntax, you can actually look at the maybe look at the lecture over there. How do you prepare from the labs? Well, I would say, assuming that you know, because all the solutions are made available, you should really go for a solution, and especially for lab number 2, we cover in 2 programming tests. So the idea about post condition should be quite clear to you. You want to review the concept about post condition and review the solution again. And also we did also the highlight lecture for lab number 1. You should also review them. And for lab number 3, you should really try to look at how the same property are being checked on different versions of the program, and see how they are satisfied and they are not satisfied, right? Things like that. And I also just posted the solution for lab number 4. So what you really want to watch out for is this one here. Okay, so for lab number 4, so you want to pay attention to invariance property being checked. You may not be asked to actually encode the whole Sudoku game in the exam. I don't think so. But you may want to look at how the invariant condition is being checked, and then maybe try to even run the solution yourself. Okay. Yeah, if you want tips for I think the example question there will definitely help. You want to focus, you want to pay attention to program verification, and then look at how the correctness condition are being formulated. And you already saw one example there. You can try more. And also for the proof, you can you already got some sophisticated one as one example. You can definitely try them out on your own after understanding the solution. And for LTL, you also want to look at the different formulation, right? The definition for the different operators. If I give you different nesting, you should be able to do it. And also, if I give you a new diagram for the LTS, label transition system, and ask you to check some property about it, you should be able to prove or disprove it, right? By giving the witness, or maybe by going through the different patterns for the path. So I think that the tips will be focus more on what we have talked about in the class, right? So everything on the question there is going to be based on them. Okay, go over solution for S2, exercise 7.1. Okay, let me see. One moment. Okay, 7.1. Which one do you want me to go over? P until R. Okay. Okay, P until R over here. Okay. As you can see over here, since we are starting from S2, so we don't have many choices. It's basically just S2 and then S2 and then S2, etc. over here. Okay. And you can see that S2 over here, implicitly, it does not satisfy P, and also it does not satisfy Q. So this is relevant to us, right? You can see P is not satisfied. And then we want R is actually satisfied right away, right? So here you want to go back to some earlier exercise on the until operator. Okay, so here R is satisfied right away. For example, let's say this is first states. That one satisfy R right away. But as for the until operator, what about P? P should be really satisfied from 1 until I minus 1. Right? Why P is considered as satisfied from states 1 to I minus 1. You can think about a 1 here is really I. Right? So this is the part I would like you to maybe go back to the lecture and then review that. Okay, so that one is going to give you the answer. So I think that part there should really is really worth your time reviewing. Okay, very good. All right, any other questions? Excuse me. Yeah, I wouldn't really comment about how many nesting. Maybe you pushed me to say some number. Did I say 5 or 6? I don't remember. But so it doesn't matter how many I might want you to nest, because you just gotta apply the formulation accordingly, right? All right. Question.
So I have a couple of questions.
Mm-hmm.
So what would be the witness for path satisfaction? Is it always a state?
The witness for path satisfaction. So depending on what you want to do, right? If you want to disprove universal quantification on a path, in that way, of course, the witness will be a state.
Because based on the definition, like, I would probably guess that it's a path suffix, but you're saying it would be a state, right?
Mm-hmm. A state. So somehow, well, let's say, for example, if you talk about the future operator, and or let's say the global operator, if you say the path satisfies maybe global phi, in that way you want to find the states that's going to violate that global property. In which case, you can suggest which state it is.
Also, for regarding the programming test, are we supposed to like write algorithms similar to the programming test?
You may not be asked to write as long algorithm like in the programming test, but since you already have done assignments and also the two programming tests already, so you can it's possible we may want you to write something on the paper, but may not be to the same scale like in the programming test. Especially for assertions, I think it's important for you to know how to write the assertions. Okay, good. How many questions? To be honest with you, I'm still finalizing it. But I think what I said in the last class was since you guys got 3 hours, right? So I think you'll be given enough. Yeah, somehow numbers doesn't really matter, right? Because sometimes if I tell you 5 questions there or 3 questions there, and each question might have sub questions, right? And also depending on the complexity of each question, it might take you a different amount of time. So yeah, I don't have the precise answer just yet.
Professor, for the last YouTube video that you uploaded,
yeah,
I think it's not complete.
Yeah, so yeah, for that one there, yeah, so I know that. So for that one there, so this one here, it's basically almost complete, and except for the very last part when I spoke about that proof correctness condition for the loops. So that's why I put it here, right? So this is actually from the previous year, starting from 5311. If you want to catch up with that part, you can feel free. But I thought, for those of you who might just be okay with looking at the notes or slides, you don't need to watch the recording. I think that part there is only about 10 or 15 minutes.
So this would be the part to study that's also related to the sample exam question, right?
That could be related, yes, of course. But if you look at the slide, for example, you can see the correctness condition for loops is definitely covered. Yeah.
Okay.
Mm-hmm. All right.
I asked about the
Yeah.
natural language example you have in the slide.
The example on the slides? What example? Sorry.
I think it's 7.1. No, sorry, it's in lecture 19.
So lecture 19. So Ferris, are you talking about this lecture here?
Yeah, I think so.
Okay, so are you talking about exercises on the iPad notes or on the slides?
Yeah, iPad notes.
Okay. Okay, let's see. Are you more referring to...
This one.
Sorry, not this one here. This one?
No, this one. The previous one, the ice mode.
This one here?
Yeah.
That one, I think we already got it, actually. Okay, I tell you where. I think that one there is actually covered maybe in 20. Yeah, I'll show it to you. And that one there, I think it's on the slides anyway. Because in the iPad note, I was just trying to discuss, different solution leading you the way. I think that's the one, right? So in the beginning, in the beginning of that lecture there, I think that's the actual solution.
I just wanted to ask if I can we like play with LPL formula? For example, can release be used into it? Like me being 22 release is the ice mode?
You mean rather than using until, you mean you want to use a release operator?
Yeah, I just wanted to see if that was it.
That one there, of course, you want to think. Well, of course, in the actual exam, if you decide, okay, let me put it this way. Okay, you want to actually think about. Okay, in this way here, right? Just in general, if you actually got, let's say, phi 1 until phi 2, versus if you say phi 2 releases phi 1. Okay, we know that these two are not exactly the same. Okay, so you want to look at the formulation there, but the main thing is, so here, let's say I smoke, right? And this one here will be I smoke. So think about something like this. There's a timeline over there. So here, until, so phi 2 is about I was 22. So let's say I was 22 over here. And of course, one thing we got to clarify, of course, from the question there, or maybe there's some explicit assumption you have to make on the exam paper, that maybe that's something we kind of expect you to do. If you choose the until version there, so that means we don't really insist that you don't really let's say this. It's really about at this point over here, at this point. At this point where phi 2 is true, should phi 1 be true at the same time? So that would be your main consideration. That's really the main difference between the until and also the until and the release operator. If you think that should be yes, they should be true at the same time, then of course you got to choose a release. If you don't think that should be the case, then you may choose a until operator. If the question itself didn't really make it explicit, in that way, you can maybe write something and then maybe put some explicit assumption about what you think should be the way to go, and then say, since, for example, I believe at this at the same time, at this future point over here, both properties should be satisfied. So that's why I have chosen a release operator. Otherwise, if you don't think they should be satisfied at the same time, then you will choose the until operator.
Alright, okay, I see.
Yeah. Good. Yeah. All right. Any other questions? All right. Yeah, so as I said, for this particular question over here about nesting the binary and unary, I will give you guys the solution to that after the review session. I'll try to post a recording as well at the same time. Yeah.
Professor?
Yeah.
When can we expect our programming test to mark that?
Yeah, I'm still expecting one TA to get back to me, hopefully by the end of today. So I'm hoping that I can get it back to you maybe tomorrow. I'm hoping. If not tomorrow, definitely very shortly after the exam. But don't worry, I'll give you guys just the same, like last time. So you can take a look at the feedback, and then if you actually want to submit any regrading request, you can do so as well. And then after that, we can look at that again. Similar procedure. Yeah, I'll try my best to really get it maybe released tomorrow. I cannot guarantee, but I'll try my best.
Also, just one last question. For the programming questions on the test,
Yeah.
The difficulty would be more similar to test 1 or test 2?
Test 1 or test 2? Oh, I see what you mean. I think for algorithm, on the exam paper, it's not going to be like a programming test 1 or 2, because as I said, it's more like a paper test. if we do want to write some code, it's not going to be that complicated. Okay, so I don't think the algorithm part is going to be as complicated as programming test 1 or 2. However, for the assertion, right? So in which case you're going to write some predicates to really to be as complete and as appropriate as possible. So that one they definitely want to review your lab number 2. So it could that one definitely will expect like a sophisticated assertion to be written whenever applicable.
Okay, and it's the same assumption that for writing post conditions, we only use the input and the output and no temporary variables.
That's correct. Yeah. So if, for example, if the question itself might just say you have to use certain variables, right? But the principle, you're right, should be only use the input and output. You shouldn't use any like a program variable you declare on your own.
Okay, thank you.
Mm-hmm. Yeah, that's right. If there are questions where we expect maybe Pascal syntax from you, we'll tell you that explicitly in the exam question. Yes, that's correct. All right. If no further questions, then we'll end the session now. I'll pause for one moment, just in case. All right, thank you so much. And then I will get a material release maybe a little bit later this afternoon. And then I'll make an e-class announcement so you can take a look. And then I'll see you guys on Thursday morning then. Okay, take care. I also got office hour today. You can check the e-class announcement. Okay, thank you so much. See you later.